A wave pool with the shape of an inverted right triangular wedge has a triangular cross-section with one leg being the wall of the deep end with a height of 11 feet, and the hypotenuse being the bottom surface of the pool with a length of 61 feet, while the width of the pool is 32 feet. If the pool is being filled with water at a rate of 480 feet cubed per hour, at the instant the height of water in the pool is 2 feet, find the A, rate at which the height of the water changes, B, rate at which the length of the top surface of water changes, and C, time it takes to fill the entire volume of the pool. The pool is in the shape of an inverted right triangle so that it has the wall of the deep end and the bottom surface of the pool. And it has a width to it to give it the third dimension. The deep end has a fixed height of 11 feet, while the bottom surface of the pool has a fixed height of 61 feet. We're filling this with water. So water will be starting to fill in there, and it will take itself the shape of a triangular wedge, though not as big as the pool. The width of the pool is 32 feet, and the width of the water will also be 32 feet because it is filling the entire width. But the height of the water will be changing, so I will name that as a variable, x. And the length of the top surface of the water will also be changing. I'll label that as a variable, y. We're given the rate at which water is filling into the pool. It's 480 feet cubed per hour. Because of the units feet cubed, that indicates that's a volume rate. So V prime, or dV dt, is a positive since it's filling up and increasing the volume. 480 feet cubed per hour. We want to look at the instant the height of water in the pool is 2 feet. That'll be the x. We don't want to label that on the picture, though, because x will be changing. We just want to look at this instant to calculate our values. If we look at just the triangular cross-section of this pool, we have our water, which has a height of x and a length of y, and we have the height of the deep end of 11 feet, and we have the length of 61 feet. We have similar triangles here between the water triangle and the pool triangle. They have the same angles. I want to be able to have x and y related to each other, so I need to find the top length of the pool here. Well, the pool is a right triangle, and therefore, if we name the length of the pool L, we have one leg squared, 11 squared, plus the other leg squared, L squared, equals to the hypotenuse squared, 61 squared. (11 squared is 121, plus L squared equals to 61 squared comes out to 3,721. We can now subtract 121 from both sides, and L squared will equal then 3,600. We can take the square root of both sides, and the square root of 36 is a 6. The square root of 2 zeros becomes 1 0. And the units of length will be in feet. We're only going to keep the positive square root because it will be a length. The negative square root will be ignored. That's a constant, so that now can be labeled on the picture here as 60 feet. So in the similar triangles, we can relate the sides of the small triangle to the sides of the big triangle. They're in proportion to each other. So if I take the top surface of the small triangle, y, and put it over the height of the small triangle, x, it will equal the top of the big triangle, 60, over the height of the big triangle, 11. Cross multiplying will give us 11y equals to 60x. Now the volume of the amount of water that's in the pool, it's a triangular wedge, and it therefore has a volume that is length times width times height times 1/2. So it'll have 1/2 times the length of it, which is y, times the width of it, which is 32, times the height of it, which is x. We can simplify this by multiplying the 1/2 and the 32. That'll become 16. And then I'll write the x first and then the y. But we have a relation between x and y, and so we can solve for one in terms of the other and place it in here. So I have 11y equals 60x, and therefore y is 60 over 11 times x, and that can be placed in here. So we have 16x times 60 over 11x. Sixteen times 60 is 960. So we have 960 over 11 x squared. There's our related variables equation between the volume of water and the height of water. And we can therefore take the time derivative of both sides of that. So I have the volume equals to 960 over 11 x squared. We take the time derivative indicated by a prime on both sides. Every variable is implicit with time. The derivative of the left will be a 1 times v prime. And on the right, we bring the power down. So that'll give us 1,920 over 11. Subtract 1 from the power and then multiply by the derivative of the inside. We can now plug our numbers in here because v prime is given as 480 equals 1920 over 11 times a 2 times x prime. Now it turns out that 1920 is divisible by 480. It's actually 480 times 4. So we can divide both sides by 480 to keep our numbers smaller. And this will become a 1, and this will become a 4 over 11 times that 2. It's just a way to keep our numbers a little smaller. And 2 times 4 is 8 over 11. So now we can solve for x prime. And x prime will equal to, multiply by 11, divide by 8, 11 over 8. So x prime, which is equal to dx dt, will be 11 over 8 units of x, length, feet, over time, hours. There's part A figured out. For part B, we have that y is 60 over 11x. We can take the time derivative of both sides of that. And we have that 1y prime equals 60 over 11x prime. We can now solve for y prime by plugging in the result of x prime, which was 11 over 8. The 11s can cancel. One's in the numerator, one's in the denominator. And the 60 over 8 can reduce to 15 over 2. So y prime, or dy dt, will be 15 over 2 units of y, length, feet, over time, hours. For part C, we want to figure out the time it takes to fill the entire volume of the pool. The volume of the pool is being filled with a volume rate, v prime, for an amount of time t. The volume of the pool is a triangular wedge, so it'll be a 1/2 times the length, which we found to be 60, times the height, which is 11, times the width, which is 32. And this equals the b prime, which is 480 times t. The 1/2 times the 60 will become a 30, times the 11 times the 32 equals to the 480. The 30 can divide into the 480. It goes in 16 times, so this can cancel with this to become a 16 over here. And then we can divide both sides by 16 to reduce it a little further. So we have 11 times 32 equals to 16t. And 32 is divisible by 16, so these can cancel down to a 2. And therefore the time is 11 times 2, or 22 in time units in this problem, hours.